Welcome! In this session, we will explore an exciting problem from LeetCode, number 496, next greater element I. We'll break it down step by step, analyze different approaches, and learn how to solve it efficiently. Let's get started. In this problem, you are given two integer arrays, nums1 and nums2, where nums1 is guaranteed to be a subset of nums2. Your task is to find the next greater element for each element in nums1 by looking at its position within nums2. Specifically, for each element in nums1, you need to find the first element to its right in nums2 that is larger. If no such element exists, you should return -1 for that position. The result should be an array called answer, where each value corresponds to the next greater element for the respective element in nums1. The input constraints specify that nums1 can have a length of up to nums2's size, and nums2 itself can be as large as 10,000 elements, with all elements being unique. Let's look at an example to understand this better. Suppose nums1 is 412 and nums2 is 1342. The output is -1 3-1. Why? For nums1, 0 equals 4. If we search to the right of 4 in nums2, there is no greater element, so the result is -1. For nums1, 1 equals 1, the next greater element in nums2 is 3, which comes immediately after 1. For nums1, 2 equals 2, there is no greater element to its right in nums2, so the result is -1 again. This gives the final array, -1 3-1. Now consider another example where nums1 is 2 4 and nums2 is 1 2 3 4. The output here is 3-1. For nums1, 0 equals 2, the next greater element in nums2 is 3, which is the first number to the right of 2. For nums1, 1 equals 4, there is no greater element to its right in nums2, so the result is -1. This demonstrates that the solution must carefully search to the right within nums2 to find the required value, or return -1 if no such value exists. In a third example, nums1 is 135 and nums2 is 6 5 4 3 2 1 7. The output is 7 7 7. For nums1, 0 equals 1, the next greater element in nums2 is 7, which comes far to the right of 1. For nums1, 1 equals 3, the next greater element is also 7. Similarly, for nums1, 2 equals 5, the next greater element is again 7. This highlights that the next greater element does not have to be immediately adjacent, and the algorithm must efficiently look through nums2 to find the correct answer. To summarize, all elements in nums1 and nums2 are unique, and nums1 is always a subset of nums2. The problem also includes some edge cases. For instance, if nums1 contains a single element, like nums1 equals 2, and nums2 equals 2 3 1, the output would be 3, as 3 is the next greater element. If all elements in nums1 have no next greater element, such as nums1 equals 4 5, and nums2 equals 5 4, the output would be -1-1. Additionally, since nums2 can be as large as 10,000 elements, the solution must be efficient to handle large arrays within the given constraints. To solve the next greater element I problem, one approach we can consider is the brute force method. The idea here is straightforward. For each element in the array nums1, we locate its position in nums2. Once we find it, we look at all the elements to its right in nums2 to identify the next greater element. If no such element exists, we simply return -1. The steps are as follows. First, for each element in nums1, find where it appears in nums2. Then, iterate through all the elements to the right of that position in nums2. The moment we find an element larger than the current one, we return it. Otherwise, we return -1. While this approach is simple to implement and easy to understand, it's highly inefficient for large datasets due to its quadratic time complexity. Each element in nums1 requires us to search through part of nums2, leading to many redundant comparisons. This inefficiency makes the brute force method impractical for larger inputs. A more efficient solution involves using a monotonic stack. The intuition here is to process nums2 from right to left, which allows us to efficiently determine the next greater element for each number. A key observation is that the next greater element for any number depends only on the elements to its right. To exploit this, we can use a stack to maintain a decreasing sequence of potential next greater elements as we traverse nums2 in reverse. Here's how it works. As we iterate through nums2 from the end, we remove elements from the stack that are less than or equal to the current number, as they cannot be its next greater element. If the stack isn't empty after this, the top of the stack is the next greater element. Otherwise, there is no greater element, so we map it to -1. We store these mappings in a hash map for quick lookup. Once this preprocessing is complete, we can simply retrieve the next greater element for each number in nums1 using the hash map. This approach is not only faster but also avoids redundant comparisons. The time complexity is linear because each element is pushed and popped from the stack at most once, and the space complexity is proportional to the size of nums2, as we use a stack and a hash map. The monotonic stack approach was chosen because it's both efficient and scalable, with a linear time complexity that makes it well suited for large inputs. By leveraging the stack and hash map, we avoid unnecessary comparisons and ensure that each element is processed in a streamlined manner. Another approach that could be considered involves sorting. The idea here is to pre-compute the next greater element for all unique numbers in nums2 using a sorted data structure like a balanced binary search tree. This involves inserting elements into the tree as we iterate through nums2 and using the tree to find the smallest number greater than the current one. Like the monotonic stack approach, we would store these mappings in a hash map for quick lookups when processing nums1. However, this method has a higher time complexity of n log n due to the use of tree operations. While it's a valid alternative, it's not as efficient as the monotonic stack approach, especially when working with larger inputs. Additionally, the implementation is more complex, requiring careful handling of the sorted structure. The monotonic stack approach stands out as the most practical solution due to its simplicity, efficiency, and scalability. By processing nums2 in reverse and maintaining a stack of potential next greater elements, we ensure that every element is handled in constant time on average, resulting in an optimal n time complexity. The use of a hash map allows us to retrieve results for nums1 in constant time, making the solution highly performant even for large arrays. Compared to the brute force method, this approach avoids redundant comparisons, and unlike the sorting-based alternative, it achieves better performance and is easier to implement. While the monotonic stack approach does require additional space for the stack and hash map, this is a reasonable trade-off given the significant time savings. Overall, this method provides an elegant and efficient solution to the problem, balancing clarity and performance to handle both small and large datasets effectively. To solve the problem of finding the next greater element, we are given two arrays, nums1 and nums2. Every element in nums1 is distinct and is guaranteed to exist in nums2. Our goal is to identify, for each element in nums1, the first greater element that appears to its right in nums2. If no such element is found, we return -1. To approach this efficiently, we use a monotonic decreasing stack. The idea is to pre-process nums2, storing the next greater element for each of its elements in a hash map. This pre-processing step will allow us to quickly determine the result for nums1 without repeatedly traversing nums2. First, we initialize an empty stack and a hash map called next_greater. As we iterate through nums2, we compare the current number with the top of the stack. If the current number is greater than the top of the stack, it becomes the next greater element for the stack's top. We pop the stack, store this relationship in the hash map, and continue. Any elements left in the stack by the end of the traversal have no next greater element, so we assign them a value of -1 in the hash map. Once we've completed pre-processing nums2, we move on to building the result for nums1. We initialize an empty result list. For each element in nums1, we use the pre-computed next_greater hash map to quickly find its next greater element in nums2. This is an O1 lookup operation for each element. We append the corresponding next greater element to the result list. Finally, we return this result list as the output. The key insights from this approach are the use of a monotonic stack, which ensures we can efficiently process the elements of nums2 in linear time, and the hash map, which allows constant time lookups for nums1's elements. Together, these structures provide an efficient solution with an overall time complexity of n plus m, where n is the size of nums2 and m is the size of nums1. Let's take a closer look at the data structures and their roles. The stack is used to store elements of nums2 for which the next greater element has yet to be determined. It is maintained in a decreasing order of values, which ensures that when we encounter a larger element, it can be efficiently matched with all smaller elements in the stack. The hash map, on the other hand, is used to store the pre-computed next greater elements for all elements in nums2. This allows us to process nums1 in constant time per element. The efficiency of this approach lies in its linear time complexity for traversing nums2 and the quick lookup of results for nums1. The space complexity is also efficient, requiring O(n) space for both the stack and the hash map. With this foundation, we can now look at how the algorithm is implemented in code. Here's the Python implementation of the algorithm. First, we pre-process nums2 using a monotonic stack. We initialize an empty stack and an empty hash map called next_greater. As we traverse nums2, for each number, we check if it is greater than the top of the stack. If it is, we pop the stack, and the popped element's next greater element becomes the current number. We record this in the hash map. The current number is then pushed onto the stack. After traversing nums2, any remaining elements in the stack have no next greater element, so we assign them a value of -1 in the hash map. Next, we build the result for nums1. For each element in nums1, we look up its next greater element in the hash map and append it to the result list. Finally, we return the result list. For example, given nums1 is 4, 1, 2, and nums2 is 1, 3, 4, 2, the function will output -1, 3, -1, as we will now demonstrate step by step. Let's walk through the example with nums1 equals 4, 1, 2, and nums2 equals 1, 3, 4, 2. First, we pre-process nums2. We start with an empty stack and hash map. For number equals 1, the stack is empty, so we push 1. Next, for number equals 3, since 3 is greater than 1, we pop 1 from the stack and record next_greater, 1 equals 3. We then push 3 onto the stack. For number equals 4 is greater than 3, so we pop 3 and record next_greater, 3 equals 4. We then push 4 onto the stack. Finally, for number equals 2, since 2 is less than 4, we simply push 2 onto the stack. At the end of the traversal, the stack contains 4, 2. These elements have no next greater element, so we record next_greater, 2 equals -1 and next_greater, 4 equals -1. The resulting hash map is 1, 3, 3, 4, 4, -1, 2, -1. Using this, we process nums1. For 4, the next greater element is -1. For 1, it's 3. For 2, it's -1. The final result is -1, 3, -1. This implementation solves LeetCode problem number 496, next greater element I, using an optimized approach with a monotonic stack. The solution is efficient, with a time complexity of O(n), where n is the length of nums2. The function next greater element takes two lists, nums1 and nums2. It aims to find the next greater element for each number in nums1 based on the order in nums2. A dictionary, next_greater, is used to store the next greater element for each number in nums2. A monotonic decreasing stack is utilized to efficiently determine these values. The algorithm traverses nums2 in reverse order. For each number, it ensures the stack only contains elements greater than the current number by popping smaller or equal values. If the stack is not empty after this, the stack's top element is the next greater element for the current number. Otherwise, the next greater element is set to -1. The current number is then pushed onto the stack for future comparisons. Finally, the function constructs the result for nums1 by mapping each number in nums1 to its next greater element using the next_greater dictionary. This ensures the output is in the same order as nums1. This approach is both efficient and straightforward, leveraging the stack to reduce the complexity of finding the next greater element from O(n)² to O(n). The use of a dictionary ensures fast lookups, making the solution well suited for the problem's constraints. Here, we start by importing the necessary libraries and defining our solution class. The method next_element takes two integer arrays, nums1 and nums2, as inputs. The goal is to find the next greater element for each number in nums1 from the array nums2. To achieve this, we use a hash map called nextGreater to map each number in nums2 to its next greater element. Additionally, we use a monotonic decreasing stack to help efficiently determine the next greater element. The stack is implemented using a deque for optimal performance. Now, we traverse the nums2 array in reverse order. For each number, we remove elements from the stack that are less than or equal to the current number since they cannot be the next greater element. After this, if the stack is not empty, the top of the stack represents the next greater element for the current number, otherwise, the next greater element is -1. We then store this information in the next greater map and push the current number onto the stack for future comparisons. This process ensures that we efficiently compute the next greater element for all numbers in nums2. Now that we have the next greater map ready, we can construct the result for the nums1 array. We iterate through each element in nums1 and use the map to find the pre-computed next greater element. The value is directly retrieved in constant time using the map, and we store it in the corresponding index of the result array. Finally, the method returns this result array, which contains the next greater elements for all numbers in nums1. This implementation is highly efficient, with a time complexity of O, n plus m, where n is the length of nums1 and m is the length of nums2, making it suitable for large inputs. To begin solving this problem, we start with the first example, where nums1 is 4, 1, 2, and nums2 is 1, 3, 4, 2. The goal is to find the next greater element for each number in nums1 based on their positions in nums2. First, we initialize two data structures. The dictionary next_greater will store the next greater element for each number in nums2, and the stack, which is initially empty, will help us track numbers in a monotonic decreasing order. Now, we process nums2 in reverse order. Starting with the first iteration, the number is 2. Since the stack is empty, there is no greater element for 2, so we assign next_greater, 2, to -1 and push 2 onto the stack. In the next iteration, the number is 4. We pop 2 from the stack because it is less than 4, leaving the stack empty again. This means there is no greater element for 4, so next_greater, 4, is set to -1, and we push 4 onto the stack. For the third iteration, the number is 3. Here, the top of the stack is 4, which is greater than 3, so we set next_greater, 3, to 4 and push 3 onto the stack. Finally, for the fourth iteration, the number is 1. The top of the stack is 3, which is greater than 1, so we assign next_greater, 1, to 3 and push 1 onto the stack. By the end of this process, we have correctly identified the next greater elements for all numbers in nums2. After finding the next greater elements for nums2, we can now build the result for nums1. For each number in nums1, we simply look up its next greater element in the next_greater dictionary. For 4, the next greater element is -1. For 1, it is 3, and for 2, it is -1. Therefore, the result for nums1 is -1, 3, -1. Now let's move to the second example, where nums1 is 2, 4, and nums2 is 1, 2, 3, 4. We start by reinitializing our data structures. The next_greater dictionary is reset to empty, and the stack is cleared. These will help us as we process nums2 in reverse order again. In this second example, we process nums2 in reverse order to determine the next greater elements. Starting with the first iteration, the number is 4. Since the stack is empty, there's no greater element for 4, so we set next_greater, 4, to -1 and push 4 onto the stack. In the second iteration, the number is 3. The top of the stack is 4, which is greater than 3, so we set next_greater, 3, to 4 and push 3 onto the stack. For the third iteration, the number is 2. The top of the stack is 3, which is greater than 2, so we assign next_greater, 2, to 3 and push 2 onto the stack. Finally, in the fourth iteration, the number is 1. The top of the stack is 2, which is greater than 1, so we set next_greater, 1, to 2 and push 1 onto the stack. With this, we've determined the next greater elements for all numbers in nums2. Now, for nums1, we look up these values in next_greater. For 2, the next greater element is 3, and for 4, it is -1. Thus, the result for nums1 is 3, -1. In the third example, nums1 is 1, 3, and nums2 is 3, 1, 4, 2. We begin by initializing an empty next_greater dictionary and a stack. Then, we process nums2 in reverse order, starting with the first iteration where the number is 2. Since the stack is empty, there's no greater element for 2, so we set next underscore greater 2 to -1 and push 2 onto the stack. Next, in the second iteration, the number is 4. We pop 2 from the stack because it is less than 4, leaving the stack empty. This means there's no greater element for 4, so next underscore greater 4 is set to -1, and we push 4 onto the stack. For the third iteration, the number is 1. The top of the stack is 4, which is greater than 1, so we assign next underscore greater 1 to 4 and push 1 onto the stack. Then, in the fourth iteration, the number is 3. We first pop 1 from the stack because it is less than 3. The next top of the stack is 4, which is greater than 3, so we set next underscore greater 3 to 4. After determining the next greater element for 3, we push it onto the stack, resulting in stack equals 4, 3. Now, we build the result for nums1 using the next underscore greater dictionary. For 1, the next greater element is 4, and for 3, it is also 4. Therefore, the final result for nums1 is 4, 4. By following this process with a monotonic stack, we efficiently solve the problem for any given nums1 and nums2 arrays. To analyze the time complexity of our solution, let's break it into two parts, building the next underscore greater dictionary using nums2, and constructing the result array using nums1. First, when building the next underscore greater dictionary, we traverse the nums2 array in reverse order. This traversal alone takes n time, where n is the length of nums2. During this traversal, we utilize a stack to maintain the next greater elements. Each element in nums2 is pushed onto the stack exactly once, and it is only popped when a smaller or equal element is encountered. This means that each element is pushed and popped at most once, making the total stack operations n. Combining the traversal and stack operations, the total time complexity for building the next underscore greater dictionary is n. Next, for constructing the result array using nums1, we perform a dictionary lookup for each element in nums1. Since dictionary lookups are O1 operations, and nums1 has m elements, this step takes m time. Altogether, the time complexity for our solution involves n for processing nums2 and m for processing nums1. Now that we've broken down the individual steps, the total time complexity of the solution becomes the sum of the two parts, n for building the next underscore greater dictionary and m for constructing the result array. Therefore, the overall time complexity is n plus m, where n is the size of nums2 and m is the size of nums1. Moving on to space complexity, let's consider the three main contributors: the stack, the next underscore greater dictionary, and the result array. The stack is used to store elements of nums2 during traversal. In the worst-case scenario, where nums2 is sorted in decreasing order, all elements of nums2 may end up in the stack simultaneously, requiring n space. The next underscore greater dictionary, which stores the next greater element for each unique number in nums2, also requires n space. Finally, the result array, which holds the output for nums1, takes m space since it matches the size of nums1. These three components together determine the space complexity of the solution. Adding up the contributions from the stack, the next underscore greater dictionary, and the result array, the total space complexity of the solution is n plus m, which simplifies to n plus m. To understand why this is efficient, let's compare it to the brute force approach. In the brute force method, for each element in nums1, we iterate through nums2 to find the next greater element. This results in a time complexity of m*n, which can become prohibitive for large inputs. Additionally, the brute force method requires no extra space beyond the input and output arrays, making its space complexity 1. On the other hand, the optimized approach, which uses a monotonic stack and a dictionary, pre-processes nums2 and n time and then computes results for nums1 and m time, leading to an overall time complexity of n plus m. While the space complexity of the optimized approach is n plus m, the time savings make it a much better choice for large inputs. To further solidify our understanding, let's analyze the best, worst, and average case complexities. In the best case, where nums2 is already sorted in ascending order, each element is pushed onto the stack once, resulting in n stack operations. In the worst case, where nums2 is sorted in descending order, each element is pushed and popped from the stack exactly once. Even in this scenario, the total time complexity remains O, n plus m. For average cases, where nums2 is arranged randomly, the number of stack operations typically falls between the best and worst cases, but the total complexity remains O, n plus m, due to the pre-processing of nums2 and the efficient dictionary lookups for nums1. Finally, a quick mathematical justification for the big O analysis confirms this. Since each element in nums2 is pushed and popped from the stack at most once, stack operations are O, n. Dictionary lookups and result array construction for nums1 involve O, m operations. Adding these together gives the total complexity of O, n plus m, which holds across all cases. When solving this problem, there are several common mistakes to watch out for. First, neglecting edge cases is a frequent issue. For example, if nums1 or nums2 is empty, or if elements in nums1 don't appear in nums2, this can lead to runtime errors or incorrect outputs. To address this, always validate the input and handle these edge cases explicitly. Another mistake is relying on nested loops unnecessarily. A brute force approach that iterates through all elements of nums2 for each element in nums1 can result in O, n squared, time complexity, which is inefficient for larger inputs. Instead, you can use a monotonic stack combined with a hash map to achieve O, n, time complexity. Additionally, some solutions mistakenly assume that nums1 is sorted or that it matches the order of nums2. This assumption can lead to incorrect results because nums1 may not follow the same structure. To avoid this, dynamically map the elements of nums1 to their positions in nums2. Finally, altering the input arrays during processing, such as sorting or modifying their contents, can cause errors, especially if those inputs are expected to remain intact for other operations. It's better to work with copies or use non-destructive methods when processing the data. Another frequent pitfall is misinterpreting what the problem means by next greater element. Some solutions compare an element to all elements in nums2, instead of only those to its right, which violates the problem constraints. To avoid this, ensure your logic carefully adheres to the rules for identifying the next greater element. This problem is often used in interviews to evaluate your ability to optimize from a brute force approach to a more efficient solution, such as one using stacks and hash maps. Make sure you can explain the intuition behind using a monotonic stack. For instance, the stack helps maintain potential greater elements for elements to the right, and its structure ensures that you can process the array in linear time. Additionally, be prepared to discuss the time complexity trade-offs between different approaches, such as why the stack-based solution is O, n, while the brute force approach is O, n squared. It's also valuable to understand how the problem can vary, like finding that next smaller element or solving for circular arrays where nums2 wraps around. Lastly, always clarify constraints with the interviewer, such as whether duplicates are allowed in nums1 or nums2, to ensure your solution aligns with the problem requirements. There are several related problems that you can practice to deepen your understanding of this topic. The most relevant is LeetCode 496, which is the classic next greater element I problem. Beyond that, LeetCode 503 introduces a variation where the array is circular, meaning you need to consider nums2 wrapping around. LeetCode 739, daily temperatures, asks you to find the next greater temperature for each day, and it also relies on the monotonic stack technique. Another related problem is LeetCode 901, online stock span, which involves analyzing stock prices over time using a similar stack-based approach. There are also alternative methods to solve the original problem. The brute force approach, while straightforward, involves comparing each element in nums1 with all elements to its right in nums2, leading to a time complexity of O, n squared. This method is simple but inefficient. The optimal solution uses a monotonic stack to process nums2 and a hash map to store the next greater elements, reducing time complexity to O, n. In some specific cases, such as when nums2 is sorted, you could use binary search to find the next greater element for each nums1 element. However, this approach is limited by the requirement of sorted input and has a time complexity of O, n log n. Each approach to solving this problem comes with its trade-offs. The brute force method is simple and easy to understand, making it a good starting point for smaller inputs. However, it's highly inefficient for larger datasets due to its O, n squared, time complexity. On the other hand, the monotonic stack approach is both optimal and the most frequently tested in interviews. It requires a solid understanding of how stacks and hash maps work together to efficiently solve the problem in O(n) time. This approach is versatile and can handle a variety of scenarios. Binary search offers another alternative, but it's only suitable when the input array nums2 is already sorted. While it achieves a time complexity of O(n) log n, it's less flexible for general cases, as most problem variations don't guarantee sorted input. Understanding these trade-offs will help you choose the best solution for the given constraints and justify your approach during coding interviews. Great job! We've summarized the problem, analyzed the brute force solution, and discussed its limitations. Keep practicing and experimenting with optimized approaches. Thank you for watching, and stay tuned for more problem-solving tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!